The concept of enthalpy relates to the flow of energy during a chemical process. Mass times specific heat constant times the change in temperature is one way to calculate the enthalpy of a reaction. Another way to calculate the enthalpy of a reaction is to take the potential energy of the products and subtract the potential energy of the reactants. For exothermic processes, energy is released to the surroundings. This results in a negative value for delta H. The negative sign simply means energy is released to the surroundings. For endothermic processes, energy is absorbed from the surroundings. This results in a positive value for delta H. A positive sign means energy is absorbed from the surroundings. Let's take a look at these two potential energy diagrams. Each diagram represents a different chemical reaction. One reaction is exothermic, the other is endothermic. To identify which is which by using the diagrams, you simply have to compare the energy of the reactants to the energy of the products. First off, let's identify the general characteristics of these diagrams. Notice that each start with the reactants, which have a certain amount of energy. Then there is a hill or a peak before finally ending with the products, which also have a certain amount of energy. We need to talk about the peak in these energy diagrams. In order for a reaction to occur, a certain amount of energy must be put into the system. An example of this would be making a campfire. Stacking wood into a fire pit does not result in a campfire. In order for the logs to combust, an initial amount of energy must be applied. This is usually in the form of a match or some other type of kindling. However, once this initial amount of energy is supplied, the logs will continue to burn spontaneously. The hill or hump on these energy diagrams is analogous to this match or the kindling. The energy required to start a chemical process is called the activation energy. The activation energy can be determined by finding the difference between the energy of the reactants and the energy at the peak of the hump. The activation energy for the diagram on the left is 50 kcals. This is determined by taking the energy from the peak, 60 kcals, and subtracting the energy of the reactants, 10 kcals. The activation energy for the diagram on the right can be found by taking the energy at the peak, 60 kcals, and subtracting the energy of the reactants, 40 kcals, which gives you an activation energy of 20 kcals. So, which diagram represents an endothermic process and which an exothermic process? To determine this, we simply need to read the diagrams and find the difference in energy between the products and the reactants. So in the diagram on the left, the products have an energy of 40 kcals, while the reactants have an energy of 10 kcals. So the enthalpy for this process is a positive 30 kcals. A positive value for delta H represents an endothermic process. It is important to notice that an energy level diagram in which the products have a larger energy than the reactants always represents an endothermic process. In the diagram on the right, the products have an energy of 10 kcals, while the reactants have an energy of 40 kcals. So the enthalpy for this process is a negative 30 kcals. A negative value for delta H represents an exothermic process. Once again, it is relevant to notice that an energy level diagram in which the reactants have a larger energy than the products always represents an exothermic process. Now, let's take a look at your new reference sheet, which is an enthalpy table. This table gives several reactions and their enthalpies. The reactions on this table can be used several different ways. The reactions can be used as written, or the reactions could be reversed. You could multiply the reactions by a certain integer. You can also reverse a reaction and multiply it by a certain integer. Reactions on this table can also be added together. The enthalpy values for any of these reactions can also be used in stoichiometric calculations involving moles. Let's look at these 6 different ways the table can be used. First, write reaction 23 as it appears on the table. This sounds simple enough, but you have to include the enthalpy term on the appropriate side of the equation. Since reaction 23 has a positive delta H, the 6.2 kcals must be written as a reactant on the left side of the arrow. Next, we need to take 3 times reaction 4. Delta H is positive for reaction 4, which means the enthalpy value needs to be written on the reactant side, the left side of the arrow. When we multiply a reaction by an integer, we must also multiply the enthalpy value by that integer. Therefore, the reaction would be 3 waters plus 3 carbons plus 94.2 kcals of energy results in 3 carbon monoxides and 3 hydrogen gases. Let's reverse reaction 1. This simply means we flip the products and reactants. When we look at reaction 1 as written, it is exothermic, which means 67.6 kcals should go on the product side. Once we reverse the reaction, the products become the reactants and vice versa. The result is carbon dioxide plus 67.6 kcals produces carbon monoxide and 1/2 oxygen gas. Now, let's take 2 times the reverse of reaction 14. When we do this, we have to multiply everything in the reaction, including the enthalpy value, by 2, then flip the products and the reactants. In this case, 2 carbon monoxide gases plus 52.8 kcals gives 2 carbons plus 1 oxygen gas. We can also do stoichiometry with the enthalpy values that are given in the table. So using reaction 42, how many kcals of heat could be produced by burning 5.8 grams of hexane? Well, if we look at reaction 42, we can see that burning 1 mole of hexane produces 995.01 kcals of heat energy. We can use this as a conversion. Now, we don't have a mole of hexane, we only have 5.8 grams of hexane. Sounds like we're going to have to follow the stoichiometry game plan. Start with what's given, 5.8 grams of hexane, and then set up your train tracks. Choo-choo! Convert grams of hexane to moles of hexane using the molar mass of hexane, 86 grams per mole. From here, we can convert from moles of hexane to kcals of energy. We know for every mole of hexane, 995.01 kcals of energy is released. Solving the problem gives 67.1053 kcals, but we can only have 2 sig figs. Therefore, the answer is 67 kcals of heat. Now it's your turn. Use reaction 40 to determine how many kcals of energy are produced when 12.6 grams of butane are burned. Pause the video. Try it out. When you think you have it, press play and check your work. You should have gotten 149 kcals. Your answer is limited to 3 significant figures.